Hello everyone, welcome back to my YouTube channel of Learning Mathematics. Myself Dr. Gautam Haldar. In this video lecture, I'll talk about the following 5 points related to the concept of relation. And the points are this. First one is equivalence class, the examples of equivalence class, results on equivalence class, partition of a non-empty set, and results on partition. Okay, let's start. First point is equivalence class. Suppose rho is an equivalence relation. Defined on a non-empty set. Let A belongs to A. We define box A. It is also be denoted by class of A. It is nothing but a subset of A such that X is related to all those elements of A which are row related to A. And this set is called equivalence class of A. This set is called an equivalence class of A. Or you can say row equivalence class. Row equivalence class of A. Okay. Now, it is clear that A belongs to class because A is related to A as rho is an equivalence relation. As rho is an equivalence relation. So, box A is non-empty for all A belongs to A. Box A is non-empty for all A belongs to A. Okay. Next one, if this is my first observation. Second observation is that if B belongs to box A, then box B is equal to box. This is also trivial that you can check easily. Okay. Now come to the next point. Some examples of an equivalence. Suppose our A is equal to set of all integers. Define a relation rho on set y. A rho B is an only A minus B is divisible by. Then in the previous video lecture we have seen that this relation rho is an equivalence relation. So rho is an equivalence relation on set. Now let us try to find out the equivalence classes. Okay. We find the equivalence class of 0. This is nothing but X belongs to set such that X is related to 0. That means X belongs to set such that X minus 0 divisible by 5. That means X belongs to set such that X is equal to 0 plus some 5k or some k belongs to z, right? So in this set, the elements are, if I put k value equal to 0, then we get 0. Then if we put plus 1, then we get 5. If we put minus 1, then minus 1. These are the elements of this class 0. Similarly, class 1 will be, the elements of say class 1 will be like this, such that x is equal to 1 plus 5k, k belongs to z. So elements are 1 plus minus 5, 1 plus minus 6, etc. Similarly, 2 plus minus 5, 2 plus minus 6, sorry, this will be 10, this will be 10, okay, etc. Then plus 3 will be 3 plus minus 5 plus minus 10, etc. 4 plus minus 5 plus minus 10, etc. Since 5 belongs to this class, and we have already seen that if an element, say if B belongs to class A, then class B is nothing but class A. We have seen previously. So since 5 belongs to class 0, so class of 5 will be the same as class 0. Similarly, class 6 will be the same as class 1. Similarly, all this. So these 5 classes, equivalence classes, are only the distinct equivalence classes on Z related to this equivalence relation. Okay, so these are example of an equivalence classes. Okay, next. We come to the next portion, next point, results on equivalence classes. Results on equivalence classes. First result is, suppose rho be an equivalence relation on a empty set. Let A, B belongs to A. If A is related to B, then class A. This is the first one. Number 2. If A is not related to B, related to B, then class A and class B are disjoint. Class A and class B are disjoint. Okay. Let's prove the first one. Suppose A is related to, we have to show that class of A is equal to class of. So for that we have to show that class A is a subset of class B and class B is a subset of class A. So suppose X belongs to class. Then by definition of class, we can say that X is related to A. Again, since A is related to B, by these two, we can say X is related to B. Since rho is an equivalence relation, and this implies X belongs to class B by the definition of class. So this implies X belongs to box A implies X belongs to box B. This implies box A is subset of box B. In a similar manner, if we take an element X from class B, then we can show that that element X will lie box A. So in a similar fashion, we can show that in a similar we show that box B is subset of box A, and therefore box A is equal to box A. Class of A is equal to class of B. Next one, suppose this happens, we have to show that this is equal to 5. If this is not equal to 5, suppose is not equal to 5, that means there would exist some element in the intersection of class A and class B. Let x belongs to class A intersection class B, and this implies x belongs to class A and x belongs to class B, right? And this implies x is equal to A, and this implies x is equal to 2. Okay. So from here we can say that A is equal to 2x because A is equivalence relation, so A is symmetric, and x is equal to 2. This implies A is equal to 2. But this is a contradiction to our assumption. But since we have assumed that rho A is not rho related to B, this is a contradiction. Okay. So our assumption was wrong. And therefore box A intersection box B is equal to 5. Box A intersection B is equal to 5. So what we have seen that if any two elements are related to an equivalence relation, then the equivalence, their corresponding equivalence classes will be equal, and if they are not related to that equivalence relation, then their corresponding equivalence classes are distinct. Okay. So let us come to the following observation. Suppose rho, we are not writing all these things. Suppose rho is an equivalence relation on. So first observation we have seen that is not equal to 5 for all A belongs to B. Second observation is for any two elements A, B belongs to A, either box A is equal to box B or they are disjoint, right? Third observation is A will be equal to set of all equivalence classes. A is the union of all equivalence classes. This is the third observation. We can easily check this one. Okay, we can easily check it. For that, we have to show that A is a subset of this, and conversely, this is a subset of this. Okay. Since box A is a subset of A, right? By the definition of class for all A, and therefore union A belongs to A will be a subset of A. This is clear to everybody, right? So next we have to show that A is a subset of union this. So suppose A belongs to AB arbitrary element. Therefore A belongs to class A. Okay, and this is a subset of union class A belongs to A, right? So we have seen A belongs to A, therefore A belongs to A implies A belongs to union class of A belongs to A, and this implies A is subset of union box A belongs to A. So from this and this, from 1 and 2, we can say that A is equal to union of this. So these are the observations. related to an equivalence classes. Okay. Now let us come to the next point called partition. Suppose X be non-empty set. X be a non-empty set. Let P, script P, be a collection of non-empty subsets of P, non-empty subset of X. Then this P is called a partition of X if it satisfies the following condition. Number one, okay, I'm writing here. Okay, number one is for any AI AJ belongs to P, either AI is equal to AJ or AI intersection AJ is equal to phi. This is my first one. Second one is X is equal to union AI. AI belongs to P. If these two conditions hold, then this collection is called a partition of X. It is something looking like this. Suppose this is my X. Suppose our collection P will be our collection. This one A1 is A2, A3, A3, A4, A5. So P our A1, A2, A3, A4, A5. So it is something like this. You see, any two elements of this set P are disjoint, and their union is the whole set X. Okay. So from this definition and from this observation, we can say that if rho is an equivalence relation defined on non-empty set A, then the set of all equivalence classes, forms a partition of A. So you see these two conditions, and you see this the definition of partition. So from these two conditions and the definition of partition, we can say that if rho be an equivalence relation defined on a non-empty set A, then that equivalence relation determines a partition. That equivalence relation determines a partition. Okay. Okay. Next one. Is next theorem. So in the previous observation, we have seen that an equivalence relation defined on a non-empty set A gives a partition, right? What happens if we take a partition of a non-empty set? Then regarding this partition, can we get an equivalence relation? No. This theorem tells us the following. Suppose rho is an equivalence relation on A. Suppose this is non-empty. Then the set of all equivalence classes, say row equivalence classes of A forms a partition. Forms a partition of A. Conversely, if P be a partition of X, I have taken here is A, then P determines an equivalence relation on A, and the corresponding equivalence classes are precisely the elements of A. Okay. The first one we have already seen that. We are going to prove only the second portion. That means the converse part. Proof. Converse. Suppose E be a partition of, okay, we define a relation row on A in the following way. A row B holds if A comma B belongs to B, or there exists some element B belongs to script B such that A comma B belongs to B. That means there is a relation between A and B, where A and B are coming from A. There is a relation between A and B if there exists some element B belongs to B such that A belongs to B. That means if A and B belongs to the same set B, then we say that there is a relation between A and B. Okay. Now we show that row is an equivalence relation. For that, we have to show that A is related to A or all A belongs to. And this is trivial. Suppose A belongs to A arbitrarily, B arbitrarily. Then there exists some element B belongs to P such that A belongs to B, because P is a partition, and suppose this is my A, these are the elements of, these are the elements of P, and since A belongs to A, so A must lie at least for some, then that element must lie to some members of A. Okay, and we call it the members as B. Okay, therefore A is related to A since A comma A belongs to B. And since A is arbitrary element in A, so this happens for all A belongs to A. And this implies since A belongs to A is arbitrary, therefore A row A holds for all A belongs to A. This implies row is reflexive. Similarly, suppose A row B holds. This implies there exists some member B belongs to B such that A comma B belongs to B. And this implies B comma A also belongs to B, and this implies B is related to A, and therefore symmetry, row is symmetry. Conversely, next, suppose there is a relation between A and B, and there is a relation between B and C, where A, B, C belongs to A. We have to show that A is related to C. From here, we can say that A comma B belongs to B for some B belongs to B. From here, we can say that B comma C belongs to C for some C belongs to C. So from this we can say B belongs to B intersection C, and this implies B intersection C is non-empty. And since BC belongs to P and P is a partition of A, and therefore either only these two things, one of these two things will happen, either this or B is equal to C. Since this is not happening, therefore this must hold from the definition of partition, and therefore B is equal to C. And therefore we can say that A C belongs to B, right? And this implies A is equal to C, and therefore row is transitive. So row is an equivalence relation. So corresponding to a partition of a non-empty set A, we can determine a row equivalent we can determine a equivalence relation on A. Okay. So let's stop here. Thank you.